right. So it's I just finished grading the exam basically. I'll probably by the time this is uploaded and everything, you guys should have your grades up. And unfortunately, we can't go over this stuff in class. I really would, love to be able to talk to you guys in person about this stuff, but we've got to do it through video. So here we are. So we'll try and spend an appropriate amount of time here, discussing the questions and kind of going through some stuff, and see if we can, put some thoughts on paper, I guess, and correct some of the mistakes that I saw. Some of the common mistakes, I guess I should say, some of the very common mistakes I saw on the exam while I was grading. Okay, but anyway, question 1. These questions should be the kind of gimmies. These are kind of the organic version of not fill in the blank, that's not what I meant, of multiple choice. There's multiple correct ways to do some of these, this is kind of an easy way to kind of score some points here. So in general, everybody did a really good job in this first page, although there are some things that we have to correct as we go through, and that's okay. But anyway, we'll start at the top left here and make our way. The quintessential example here, right, of adding a halogen, right, Br2, and we get some energy going in there. You could use NBS probably here too. That would be probably fine, but that's fine here, right? We get some bromine. Next, we got to do an elimination, so we pick a good base. My kind of go-to base is sodium ethoxide and ethanol. You could use T-butoxide, right? We're trying to do an SN2. We don't want to compete with an SN1. We're at a secondary carbon, right? This is a secondary carbon, so we got to worry a little bit, I guess, about SN1. You could use sodium hydroxide here. I really wouldn't. If you have access to whatever chemical you want, and there's no real competition with anything here, heck, you could use T-butoxide if you wanted also, just to make sure. You could use LDA, right? Any of these things would be just as valid here. And that would be fine. Don't pick something that's not too bulky, and don't pick a weak base, right? We're doing an SN2, so you want a strong base. You want it to be a localized negative charge. All those things that go into picking a nice, good base here, right? Next, you see we do a trans addition here of a halogen and an alcohol. This is our Halohydrin reaction, right? So in these conditions here, we want to make sure. Whoops. Sorry about that, and I clicked on the wrong one. We want to add bromine, and then we want to have some water around, right? We end up forming the bromonium intermediate along the way, right? Remember, our bromonium intermediate is that guy, right? So it's basically like an epoxide, right? So if you go back and you take a look at your halogenation reaction, not your free radical halogenation, just your halogen, Br2, right, to add to an alkene or an alkyne. It's going to go through this bromonium intermediate, it's going to behave just like an epoxide, right? So you can go back and take a look at that mechanism now, maybe with some fresh eyes. And then we got to turn this into an epoxide. Well, we need to have some sodium hydroxide in there. Whoops, man, I don't know. I think my pen is dying on me is what it is. That's not good. And then to turn a halohydrin there into an epoxide, we can add some sodium hydroxide, and we get that going, right? So there you go. That's pretty good. These are a lot of classical OChem 1 stuff right here, right? This is classical OChem 1 stuff, and then just something a little bit new there at the end with the epoxide stuff, which we briefly talked about at the start of the semester. A little bit more review here. An alcohol into a tosylate. To do this, we're going to need some tosyl chloride, TSCl, right? So let's see if I can find some space. Here we go. So tosyl chloride is this. Okay. So that chloride's really labile. It's going to be easy for something to come in there and pop that off. Although we do need a base, so we want our good old buddy pyridine around. And this is a fantastic reaction to turn an alcohol into a very good leaving group, right? This is what I want. A tosylate, an OTS group, is a fantastic leaving group. It is also stable under relatively stable under acidic conditions, and so it's a good way to kind of good way to transform an alcohol into something else without transforming it into a halogen and the susceptibilities that come with a halogen. Okay, so tosylation here let's see, red right here we get rid of our our double bond, so that's a nice simple H2 over palladium or platinum or nickel, or some of you guys I think used a rhodium catalyst there, and that's fine, whichever one, doesn't really matter. And then finally we bring in our good old buddy LAH, right? So that's lithium aluminum hydride, a powerful base, a good reducing agent, so we're going to get rid of our bonds to oxygen, right? That's kind of the name of the game with a reducing agent. And so we just end up with our simple alkane there, right? Fantastic stuff, okay? So there's another use for LAH. It's actually a very common reagent. If you go and watch the carbonyl chemistry that I've been chatting about with you guys recently, you see we use it quite a bit. And we'll use it, it's a very common reagent. Okay. Next, alcohol into an alkene. We have to, this is going to be done under acidic conditions if we want to do it in one step. So we're going to need some kind of dehydrating acid, sulfuric or phosphoric acid. And we're definitely going to have to heat this up, okay? So heat this up with some sulfuric or phosphoric and we can get rid of that. Alternatively, right, and this is why I like these types of questions. They're not my favorite questions. I'll talk about that later, but that's okay. Alternatively, you could do a tosylation here again, right? So tosyl chloride over pyridine. And then, pick some kind of strong base. And that would be just fine too. Look, the beautiful part about organic chemistry is there's multiple ways you guys can accomplish something. Some ways are more elegant, some ways are better. But there's multiple things to do, and again, if we're doing chemistry on paper, you guys have a little bit of freedom here. So that's why I do like these questions. They should be good reviews for you guys, this type of stuff. So, but anyway, there's a couple ways to do this. Here we go again. Very similar reaction to what we just saw up here. Here. So same thing. Cl2 and H2O. Now we come to something that might be a little bit tricky. Really, at the end of the day, what it looks like is all we got to do is transform an alcohol into a chlorine, but we don't want that. We don't want any migration, right? We don't want any. We want to add that chlorine specifically to that spot, which means that we can't form a carbocation. Okay. So we can't just add HCl into that because that would form a cation. Then we'd probably see a migration, and we'd end up with a geminal dihalide rather than vicinal dihalides. So we want something like SOCl2 or PCl3 would be just fine also, or PCl3. That would be okie dokie. Okay. Or alternatively, you could, well, no, that wouldn't really work too much in this case. So either one of those. Now, the beauty of these, right, is that we are not going to, they're more reactive with secondaries. We don't have to worry about SN1 really happening in either one of these cases. You could maybe do HCl and zinc chloride, but I don't know. Like I said, I'd say SOCl2 would be, if I had to pick something to do in the lab, that's what I would choose here. Okay, but the thing to recognize is that we can't have a cation, and then so remember, if you don't want to form a cation, don't have an acid around. Right, that's usually one of the indications of that. All right, so we take this same compound down here and we turn it into an alkyne. All right, there's really only one way we have of making an alkyne, and that is we take some sodium amide, NaNH2, in ammonia, NH3, and there's usually an excess of that around, and that'll do subsequent elimination reactions to get our alkyne. And so now we are under basic conditions, right? We have our terminal deprotonated alkyne there. Remember, this is just the same as this, right? Basically, we're seeing a lone pair and a negative charge there at the end, right? I just put the sodium in there to explicitly, sometimes it's hard to see negative charges on these drawings, so I just wanted to explicitly make it there for you guys. All right, so now we have an epoxide under basic conditions. What we will end up doing is this, right? Here, and then we will do that, right? So where we add those two carbons there from the epoxide, and we have an acid workup there at the end. Technically, we might have to watch out for that alkyne there when we do the acid workup, but that's okay, right? I'm not going to be that picky about this stuff. All right, so there's the colorful first page. No problems. I shouldn't say no problems. There's not too many problems that I saw in here that I really need to talk with you guys about. So it looks like you guys are doing a good job kind of memorizing the reagents and conditions to do that stuff with. So good job on that one. Okay. Next is going to be page, questions 2 and 3, and there, those videos are going to be a little bit longer because I really, I'm going to have to talk with you guys about that. Okay. But anyway, page 1, good stuff. Thumbs up, pats on the back. Okay. We'll see you guys in the next video.